Okay, I think we can get started. So, as with any lecture, I want to start with a few administrative things. So let me just show something here. Let's see. Okay, I hope people can see the screen share. Okay, so this is the student preview. This is the Blackboard, and I just wanted to point out to everyone that if you go to the course content and you go to problem sets, then problem set 1 has been uploaded. If you click on it, you can see here, and you can get problem set number 1. This, okay, just a few quick questions, mainly about how to do just very simple evaluations of the electric and magnetic fields. This is stuff that hopefully you should have already done in 2041, and it's really just to get you started. Okay, in terms of the actual submission, the recommended way is for you to just attach a file where the work that you've done, either in a scanned format, or if you do it directly off a tablet or something, save it as a PDF. Again, PDF, please, and upload them here. Right, and then pretty much click submit. There is a deadline set here, so please do do submit it before the deadline. I've also, if you go to course content again, if you've never done this before, even though I can't imagine that this is now the third term that we're teaching online or partially online, that you haven't done this before, but in miscellaneous, I've also used set up some instructions for a particular piece of software that you can use on your phone. If you have written work to make PDFs, and you can just click on your phone and then construct a PDF out of that. Again, this is just for your convenience. You don't have to use this software, but it's freely available on both the iPhone and Android. So it's something that is relatively convenient to use. Okay, but feel free to use anything you want. The only thing is, please make it a PDF. Do not submit JPEGs, just like take pictures and submit it. At least try to help us from our perspective as well. Okay, any questions about the problem set? Okay, I don't see any chat coming up, in which case we can. Oh wait, okay. Academic honesty form, yes. We will also post academic honesty form here as another assignment, and then you can upload it there. Okay. Right. There's no hard deadline, but I think at least by the end of the ad drop period, everyone should have submitted the academic honesty form. But I'll add it to as an assignment. You get 100% marks if you want. Ad drop period ended yesterday. Oh right. Okay. In that case, submit the academic honesty form by the end of the week. I'll add it to the website. There's no rush. There's no rush. Okay, so another question is, how many problem sets will we have? The aim is to have about 1 a week. So this one was a little bit late. I uploaded on Sunday, so I've extended the deadline until Sunday. But typically the aim is to get a new problem set by the end of the week. So typically after the Thursday lecture, I'll try to give out a problem set and also have a recording for the exercise class prepared by that date. This was the first time, so it was a little bit messy, but yeah. Will we resume face-to-face teaching? I have not heard anything about resuming face-to-face teaching. I don't know whether that is wise. So, and to be honest, it's not my call to make. The only thing I want to point out, and that is something that I don't know, like most of you won't be affected, but there are some who are who registered the course under the assumption that maybe they put exercise classes in a particular time, but that may end up clashing or things that are not relevant. So if we resume face-to-face teaching, if you end up getting into trouble with things, please do let me know. Although, to be honest, I actually think that at least for the exercise classes, we can keep the current structure, even if we resume face-to-face teaching. I think the current structure may actually work quite well for students. Okay, would like to know the passcode for the Zoom recording of the exercise class. There should not be a passcode. Let me check. So my screen is still shared. So this is here, cloud recordings, exercise class. Oh, okay. Seems to be working for me. Yeah, it seems to be working for me. Okay, if you still have trouble with it, let me know. I'll check it, but it seems to be okay. Okay, the other thing I wanted to okay, I don't know what that is. If that's the passcode, then it's a really, really challenging one. Okay, the other thing I wanted to at least highlight in terms of administration is that my apologies that the discussion board we haven't followed up as tightly as possible, but I promise that this will be sorted out, and we'll whatever discussion. I noticed that people have put discussions here. I'll attend, or me and the TAs will attend to this more frequently. Okay, so please do continue participating in this, and I promise we'll make the turnover time for the discussion board. We'll make it quicker. Okay, let's see. Okay, so any questions about this or any other administrative stuff before we go with the actual lecture? Okay, in that case, let's just let's just take a look at at the physics then. Let me share my screen. Okay, I hope you can see this now. Perfect. Excellent. Okay, let's get started. So let's start with a quick recap of what we did last time. And so last time we actually started off with finishing up. So we first looked at the different differential operators. Differential operators. Okay. So I hope that we all remember at least the three important ones. So we've got the gradient, we've got the divergence, and then we looked at the curl. And so you know, the thing to remember, at least the geometrical meaning, right? I can all show you the formula, and everyone should be able to just be able to plug it in. But the geometrical association is also a picture that I hope that people will at least bear in mind. So, for example, for the gradient, it's just the it's basically these are the vectors, pointing vectors. Oops, don't know why this is not working. Okay, this is technical glitch again. Let me just fix this. Okay, here we go. Let's back up. Okay, so these are the vectors that point perpendicular to a surface phi equals some c. Okay, so if you imagine that you've got a scalar field and you've got contours of equal field, sometimes you can think about it in terms of potential, so equal potential, then the gradient is simply the vectors that point perpendicular to it. The divergence is basically the amount of field flowing out of surface. Okay, or I should probably say closed surface. So if you imagine just you know, in some particular position, particular location, and you have a you know, the amount of field that goes both in and out. That's the measure of divergence. And the curl is in another way you can look at it as the amount of you know, the amount of rotation of vector field. Okay, so these are the three differential operators that we have seen so far, and for the course itself, these are the only three that we typically need to use. Now, of course, there is also a so-called Laplacian. Okay, and this is just the combination. It's a combination of the divergence and gradient. Okay, and we've actually seen examples of other combinations of differential operators and of different fields. So we've looked at, you know, how do differential operators act on sums and products of fields, and then we've looked at, you know, how to combine differential operators. And the two that are, well, let's see, combine differential operators. Okay, and the important ones, hopefully we remember which ones are the important ones. Okay, so in particular, one of the important ones are, of course, that there are two of them are actually identically zero. So we've got that the curl of a gradient equals to zero. We've got that the divergence of a curl equals to zero. Okay, and of course there is also always the Laplacian, which is just the Laplacian here, which is simply given by the gradient of the divergence. Sorry, the divergence of the gradient. Fine. And then there are two others that are simply, you know, some particular combination with some expression. Okay, so now once we've defined the differential operators, we can basically look at, you know, what is the relationship between these differential operators and the field itself. And this is where so-called Helmholtz theorem comes in. Helmholtz theorem comes in. So Helmholtz theorem basically says the following, that for any, for a vector field F, I can always express this in terms of a gradient plus a curl, where in this case phi is some scalar function, a is some vector function, and the divergence of a is specified. Okay. Now this here is then also the meaning of being able to write it in this way, and this is what we've shown last time around, is that then if the divergence, so basically if the divergence of F and the curl of F and the divergence of A are specified, then field is complete. So F is completely determined. Okay, and then finally, we then arrive at our field equations. So let me just, and then finally we get our field equations in differential form. Okay, so here basically what we've done is we've looked at the electric field, we've looked at the magnetic field, and we've specified what is the divergence, what is the curl of each of these. Okay, so this is a good moment to pause for just 1 or 2 minutes, okay, very briefly, but I want you to, at least at this point, see if you remember the field equations in differential form. Okay, so I'm going to give you a minute, take a piece of pen and paper, and see if you can just write them out. See if you can get the correct form and it's whether it's in your head or not. Okay, so we'll come back in a minute or two, but hopefully, it's something that hopefully you can try this out as we speak. Okay, I hope we've all had the opportunity, to test ourselves, see, okay, do we know what the differential operators are, E and B. So anyone want to give it a crack? How about what is the divergence of E? Anyone? Rho epsilon naught for vacuum. Correct. Yes. Here the assumption is that we're working in vacuums. Good. Okay. Okay. I see that Alex has a question. Let's do that after this quick intermission. What about the curl of E? Actually, let me write them down as we go along. So these are the field equations. Field equations. So we've got the divergence of E equals to rho epsilon naught. Let me double check if there's a minus sign. No, I don't think there's a minus. Okay, good. What about the curl of E? Zero. Good. The curl of E equals to 0. Excellent. What about the divergence of B? 0. Very good. More than one answer. 3 answers. 2 answers. Okay. What about the curl of B? Anyone? Curl of B? Mu naught J. Correct. Excellent. Okay. So indeed, the curl in this case is just mu naught J. Okay, so this is basically the set of equations, and we now know, okay, more or less how we've now more or less specified B and E completely, right? And this is why, you know, when people are even referring to this theory, it's complete. The theory is done. This is the static case. We'll do the dynamical case later, but you know, in principle, once I know the E and you know the divergence and the curl of E and the divergence of B and the curl of B, the field has been specified. So this is the point where we ended, and so I wanted to you know, for today's lecture, I want us to take a look at, you know, transforming this into the integral formulation. And basically what we're going to do is twofold. We're going to take a look at the integral forms of differential operators. Okay, the reason why there's this close connection, or why there's a one-to-one correspondence between the differential form of Maxwell's equations and there's an integral form of Maxwell's equations, is because actually the differential operators actually have an integral formulation. And last time around, we almost derived the integral forms. I didn't do it exactly because I wanted to just give you a geometrical view of these differential operators. But if we actually start from that point and we take it a step further, we actually arrive at the integral form of differential operators. And these typically are what helps us to understand the geometrical meaning. So that's the first step, and then after that, we will you know, we will end up with two theorems that are very useful. That's Green's theorem and Stokes' theorem, which basically allows us to you know, practically allows us to do, you know, volume integrals into surface integrals, or surface integrals into path integrals. But they are again very intimately related to the differential operators that we have. And then once we have established those two automatically will give us the integral form of the formulation. Now, on top of that, there was one thing last time around that I more or less kind of glossed over, and that is in the derivation of the curl of b, I actually had to make one term vanish. Well, after getting Green's and Stokes theorems out, I'll revisit that just to show to you how that part of the proof works. Okay, so let's just get started. So let's do a very quick, and this is really supposed to be a very quick um, introduction to the integration of fields. Okay, so before we even do things like expressing them as differential, expressing differential operators, let's take a look at the integration of fields. Okay, now this is something that hopefully we've all in one way or another have looked at. So let's just okay. So the first one that I wanted to just discuss are our so-called path integrals. Path integrals. And these are basically, where we end up simply summing over, we have a particular path and we end up just summing over whatever the field is that we're considering. So in this case, we have, for example, a scalar field. We can do the following. We can integrate over some path C of some phi, which is a scalar field, and dr. And this then leads to the expression that we have in the x direction, the integral of phi, and if we do x, y, z dx, and then we've got ey, the integral x, y, z phi dy, and ez, the integral x, y, z dz. Let me just add plus signs here. Okay, so this is very simply, very simple, basic. If you have a scalar field, how do I integrate over a line? And this is something that then will give me a, in this case, a vector quantity out. Okay, but the integrals here are ordinary scalar integrals that can be evaluated using ways that hopefully that you've seen. Now, a vector field, can actually be integrated in two ways. So the first integral I can do is a dotted with dr here, and here if I simply expand this, I basically get a x ex plus a y ey plus a z ez, and here I'm basically do the integral here, and then times dx ex plus dy ey plus dz ez. Okay, and this here then ultimately evaluates to the integral of ax dx plus the integral of ay dy plus the integral of az dz. Okay, so this is the dot product. Now there's another one. There's another integral we can do. So here we're looking at vector fields again. And then it's the cross product here. And so we can actually do this integral by simply looking at a cross dr. Okay, and I can again expand this as ax ex plus ay ey plus az ez cross product with dx ex plus dy ey plus dz ez. Okay, and if I now do this evaluation properly, I get something that is a vector field, so it's Ex, and now I get the integral of AY dz minus AZ dy of dx. Oops, no. Okay, this is sufficient. Okay, and I get AY, the integral of A, let me do this properly, should be AZ dx minus AX dz. Yes. And then AZ here. Integral is AX. Oops. AX dy minus AY dx. Okay. So those are all the ways in which you can integrate a line integral here. Okay, now what about surface integrals? Oh wait, actually, no. I wanted to make a quick note first when we do line integrals. So like ordinary integrals, what we have here with path integrals is they have the property that the integration path is actually an important thing. And so reversing the path also reverses the sign of the integral. So in this case here, we're just saying, if we reverse path, we reverse the sign. So this is something hopefully you've seen. So if I integrate, let's say from A to B, and let's do A, I don't know, dotted with dr, and that is minus B A of A dotted in dr. Okay, another way to look at it is now we're taking the reverse path, and so the direction of the path has flipped. Okay, now we can also subdivide the path into pieces. Okay, so basically if I integrate from A to B of, let's say, A dotted with dr, then I can simply do A and some intermediate point P of A dotted with dr plus P B A dotted with dr. Integration of fields. Okay, any questions so far? Okay, if not, then let's take a continued look at this. Now let's take a look at the surface integrals. Fields. Let's take a look at surface integrals. And the thing that I already had kind of shown or used is the concept that when you have a particular surface here, then the surface element is simply a vector quantity where the direction is normal to the plane of that surface, and then this is basically the size is just the size of this area, and this is the direction, the arrow. And so in this case, there are several surface integrals that you can consider. So for example, there is the surface integral of just, my scalar field. I can integrate a vector field using the dot product, and I can integrate a vector field using the cross product. Okay, so the only thought that you have to put in here, of course, is, okay, well, what is my surface that I'm integrating? So let's say if I have some flat surface, let's just take some, if I, for example, a surface element, and I align the surface element exactly with 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 the axis. So imagine I've got something that looks like this, and this is the up, and let's call this, this could be X and Y, and then this is Z, for example. So in that case, in Cartesian, you can simply write that ds equals E I dxj dxk. In this case, for I is not j is not k. Okay. Now I'm only here mainly showing you the Cartesian version, but we will actually later on we will also showcase or highlight um, things in curvilinear coordinates. Okay, so that is something that we will do at a later stage. Okay, finally, the let's say the volume integrals. So here, volume integrals. These are triple integrals where indeed where we're integrating over the entire particular volume. That a volume element is something that does not have a vector or does not have a direction. So we only have two types left. So this one where we integrate over the scalar field, and one where we integrate over the vector field. Indeed, in this case, the element is simply, in Cartesian coordinates, if I align the coordinates in a particular way, I can just do dx dy dz. Okay, so so this is the first part that I wanted to discuss, and I suggest we take a quick break here, 5 minutes, and then after the break we come back and we start looking at the integral form of the vector operators, and we will also start discussing Gauss's theorem and Stokes' theorem, and then moving on to the full formulation of the integral form of the fields. Okay, so let's get back at 5:16. See you guys in a bit.
Hello, hello, Professor.
Hello?
I want to ask, there's a property, just the curl of a curve A, then it has a property, then as separate to 4 terms, and then there's 2 terms that goes to 0, like the theta A times the gradient dot gradient. That term will go to 0, right?
Oh, 1 second. I hope I can follow. So you're asking when you have the curl of a curl, then you have 4 terms, and 2 of them are going to 0, you're saying?
Yes.
Why would that be? I actually don't think that's necessarily always true.
I'm just want to ask, is that a theta A times that triangle theta dot triangle theta is this term goes to 0?
Okay, it's very hard to follow when I'm trying to. Okay, I think I know what you're saying. Okay, so let me share the screen and take. Okay, we have 1 minute, so I will have to try to make this quick. And screen here. Okay. You're asking about this one here, right?
Yes.
And you're saying if you actually just do the kind of multiplication, you get 4 terms?
Use that identity, we get 4 terms. The identity that you show to us in the last, yes, this, the last one.
Okay. So you're saying if I put a nabla here,
Yes.
then I have to put a nabla here.
Yes, yes.
And here, and here, and here, here. Right. Okay.
Is that means that there's nothing after the nabla, so I'm just partial D 0, so it goes to 0.
How do I explain this in a good way? It's not like there's nothing there, but it's it operates on. Okay, let's pick this up after the lecture. Okay, I know what your question is. I'm trying to think of a best way to explain it to you.
Okay.
But yeah, let's do this after the lecture.
Okay, thank you.
Okay, let's see. Use annotation. Right. Yeah, that's something that we can do, but let's, for the in the interest of time, let's not do this. Okay, so we are now at a position, right? We've looked at how to integrate fields, which is again very straightforward in terms of things that we've known, we've seen before, and so. You know, but the interesting challenge is when we now try to look at a formulation of the differential operators in terms of an integral form. And so let's start with that. So let's take a look at the forms of vector operators. Okay, so the first one that I want to show, this is actually the gradient. The gradient is actually something that geometrically you can consider the following. Just the limit of v going to 0 of 1 over v, okay, the integral over phi around some ds. Okay. Now this is something that you can, well, these identities that you can, you can relatively easily verify in the Cartesian coordinates. I'm not going to do them all, but I think for the gradient is something that I can do. So for example, if I look at the gradient, then I can imagine a box like this, and let's use of modern technology to draw a perfect box like this. Oh, that's very clumsy. That is clumsy. Oh well, okay. I don't want to redo this. Okay, so imagine there's this box here, and so we have a phase called the x, y. Sorry, what am I doing? X, and this is dz. Okay, it's not ugly. Z, dx, y. Okay, and so in this case, what I'm trying to do is, we have these surface elements that are given by, let's say, ds. These are simply given by, for example, minus ex delta y delta z. Okay, so you've got a particular face here. So in this case, this is the one that goes in this direction. This one here is the one that goes in that direction. And so now I can take the whole field out. I can assign all the different ones. So the ones on the opposite side are, if we call this phase 1 and this is phase 2, then delta phase 2 is simply ex delta y delta z. And now know that the variation here, the variation among these two is basically phi goes to phi plus partial phi partial x. Right? So if I start in one side and I go to the other side, I basically go from some value, some canonical value phi to phi plus so partial phi partial x. And then I can do this for all sides. For all sides, then I get for all faces, I simply get phi yes. And here I just do partial phi partial x, partial phi partial y, ey. And I'll highlight exactly where these terms come from. Here, times delta x, delta y, delta z, which is simply given by the gradient of phi and some volume, delta phi here. Right? So we can see that indeed with the delta x associated with the partial x, I've got one minus sign here, I've got one plus sign here. So one of the two, the phi's cancel. The only thing that is left is partial phi, partial x. And I get this thing here. Oops, I think I should x here. And so indeed, what we get is partial phi partial x and in the direction e to the x, and I get delta x, delta y, delta z. And so in this case, indeed, all the terms have partial delta x, delta y, delta z. I get the gradient of phi in some small volume. And so indeed, if I now take this sum to be the integral, then I do end up with the definition that I wanted to get, and that is that, you know, I shrink the delta v to 0, and so in this case, this indeed goes to the limit of v goes to 0. Actually, this is just called of 1 over v, and then the loop, the closed integral of ds, right? Or basically what we've seen here at the top. So by doing constructs like these, you can convince yourself that the gradient indeed is just basically the amount of phi that goes through, right? The amount of phi that is there over some particular surface. And now you can do exactly the same, and that's something that I will not probably have not the time for, but you can also show for the other ones. So if I take the divergence, and the divergence can be shown to be the limit of v goes to 0, 1 over v integral of a ds. This, that is the divergence, and cross curl, we have that the curl of a, again, is the limit as v goes to 0, 1 over v, this is s times a. These are all intimately connected to, you know, the particular surface that I have, and then, you know, and then the direction. Now, another point here to make, and this is something that, you know, hopefully you can see, is when I look at the divergence, I'm actually looking at the vector A. Let me try to annotate this. So I'm looking at vector A that is then projected upon the surface. Imagine I've got some surface here, then, you know, whatever A is it pointing, let's say A is pointing in this direction, but let's say here locally ds is pointing in this direction, then I'm just asking, okay, how much A goes out perpendicular, or perpendicular to the surface, right? Because the dot product basically projects A upon ds, and then I integrate over the entire surface. So all that I'm asking is how much field is going out of a particular surface. Again, bear in mind that the divergence, because we've got, you know, a closed surface, so whatever comes in, if the same thing that comes in that also goes out, then, you know, the contributions cancel. Now, in the other way, here, if this is again ds, this is A. But instead of now getting the dot product, we're actually looking at the cross product, so the S and the A. So this would be something that then goes perpendicular both directions, and this would be ds cross A. And so you can imagine that if A dot ds is the element that is perpendicular to the surface, then the curl, or the cross product of ds A, is then selecting the component that goes along the surface. Okay? If you imagine a spherical surface, then it's basically just a vector component that then follows the surface perpendicular, sorry, goes along the surface. And you can also imagine that then that's also another way to consider that that is the loop. Right? It's the element, it's the flow that goes along the surface. As we're considering a closed surface, it would be something that then loops around the surface. But there is another way to formulate the last one, the curl, and that is in terms of an actual loop around a bounding surface. But we're going to leave that. Well, we've seen it before when we looked at the geometrical meaning of the curl, and we're going to look at it again through when we look at the Stokes theorem. Okay, so let me clear this out and give you a quick second to internalize this. And this is just the integral form of operators by vector differential. Okay. So let's start with with one of the first fundamental theorems that I think is important to for us to consider. The first one is Green's theorem. I don't know why it's green, but it's Green's theorem. And so Green's theorem basically states relates the divergence. Okay? It relates to the total flux of a vector field around some closed surface, and it relates it to the enclosed volume V. Okay? So let's first start with the integral form of the divergence. And instead of making an infinitesimal volume, we're actually going to split up our entire space into small chunks. Okay, let's call them I, and they have bounding volumes, bounding surfaces Si. Okay. So let's imagine the following situation. So we have raw, nice looking again. So let's imagine I've got little boxes like this. Okay, how do I draw this? Okay, so we've got one, and I'm not going to add it exactly next to it. I'm going to keep it a little bit of space so that you can tell the difference. Here are two adjacent elements, and let's call them, just give them, a superscript, subscript I. And I know for these that I can tell that the gradient Vi given by the loop integral of Si of A dot ds. Okay. Now just bear in mind and remember that this is exactly the divergence form that we looked at. Right? So, but instead of taking these volume elements all the way to zero, we're not going to do that yet. And we're going to just say, okay, we're going to try to sum up all the different adjacent elements. Now, the total divergence over this entire volume that we're considering is then simply given by total divergence is simply given by the sum I divergence of A I equals to the sum of I and then all the bounding surfaces A dot ds. Okay. Now, so indeed, if I now take the volume all the way to infinity, okay, then this thing becomes an integral. So if all these VI's goes to 0, then sum goes to integral. On both sides, we're supposed to get integrals. So let's do the following. So now we have that the integral of divergence of A sum dv equals 2, and I'm gonna butcher a little bit the notation. So I'm gonna do the integral and then another integrals of A dot ds. They're all the separate si's. They're all the i's. Okay. If there are any mathematicians here, I'm sure that they're ready to strangle me, but just a little bit of abuse of notation. Now, the realization here, especially on the right-hand side, is that the integral over all of i's, of all of these si's, actually simplifies. And you can actually see it the following. If I take a look at the first element here on the left, this thing here, then this face has the following surface pointing out, pointing normal. But the one right next to it points exactly in the opposite direction. And so even when I take a look at this vector field A, and I look at all the contributions of all these surfaces, then if there are two adjacent elements and they touch each other, then their vector, the surface element, cancels exactly. So what happens then is that this here, okay, all inner, I'm going to call this inner surface elements, here twice, but opposite side. So they all cancel. And the only surface that is left that appears once is the outer surface. And so this double integral, if you will, then finalizes to just a single integral over the bounding volume S of A dot ds. I don't know why I wrote green still. It should be Gauss's still. Too many names. Okay, this is Gauss's still. So in the end here, we have an expression of so-called Gauss's theorem. And Gauss's theorem simply states that the integral over the volume of the divergence can be expressed as the integral of this vector field A over its bounding volume, a bounding surface. And so this is Gauss's theorem, and Gauss's theorem then allows us, if you will, to write the divergence into something that looks more like an integral. Let's actually take a look at how this is applied in terms of the fields. Now I can ask, okay, so this is the integral form. Integral form of EM fields. We're just going to look at the divergence now. Again, I hope you do right alongside with me. So let's consider the electric field. Okay, we all remember what is the divergence of the electric field? Rho over epsilon naught. Now, what do we get? We get the integral of E dV equals to the integral of rho over epsilon naught dV. This here equals to the integral of some bounding surface S. The top one here, if I just take a look at the rho is the charge density, I should just get the entire charge here, right? Because the rho is just a charge. Charge density, and I'm integrating over the entire volume. So I'm basically getting 2 over epsilon naught. Okay. Now I get indeed something that I can express as E going through some surface, and that is related to the total charge inside. Again, this is, hopefully people recall, this is just Gauss's law. Okay, so the flux of E, right, the amount of E that goes out of a particular surface is related to just the total charge inside. Okay, let's take a look at the magnetic field. Magnetic field. Now, what is the divergence of B? 0. In this case, what do we have? We have that E plus B equals to 0 dV 0 equals to the double integral of B dot ds. Okay. So again, once we formulated Green's theorem, we we have all the tools. We have the exact tool that is necessary for us to identify or convert at least the differential form of the divergence into something that we know it's maybe a little bit more familiar in the integral form of Maxwell's equations. So simply by using Gauss's theorem, we have been able to convert the divergence into its integral. Okay, this is a good time to take another quick break. So let's take another 5-minute break. We'll come back at 5:47, and then we're going to look at Stokes' theorem and how to get the remaining 2 equations, Maxwell's equations, and finally we're going to take a look at the curl of B and complete the proof that we did last time. Okay, I'll see you guys in 5 minutes. Okay, welcome back. Let's continue. The next important theorem that I want to discuss is Stokes' theorem. The Stokes' theorem is actually very similar to Gauss's theorem, but it actually relates to the curl of a vector field instead of the divergence of a vector field. And so we're actually going to take a look at a result that we've seen, I think 1 or 2 lectures ago, where we're actually looking at the geometrical meaning of this curl. And in particular, what we showed was that if I take the loop, right, if I integrate a vector field around a loop, then that is related to some, some vector times the actual surface of it. So another way to look at this is, imagine I've got some loop here, and I'm integrating around it. Here, let's say I'm integrating around some loop here. Then I can actually I can relate this loop to something that is related to the surface. In particular, what we saw is that if I sum up some ci, okay, this is the actual path that I'm taking, dotted with dl I equals the curl of a times ds. Okay, so here in this case, I'm taking these 4 elements, these 4 lines. That's what I call the i's, and I integrate a along all of these lines. And that is then related to this surface where the arrow should come, let's see, the right-handed system should go down. This is the actual ds. Okay. So this is basically something, a result that we've seen as a geometrical interpretation of the curl. Now imagine I'm doing the exact same thing, but we're considering an extended surface now. Technology again. Okay. Now we do the same thing, but now we extend throughout different surfaces. Let me try to again draw this, and I'm drawing this in a little bit more exaggerated way. Imagine that I've got these loops coming in, doing this extended surface here. And for completeness, let me also draw one underneath here. So if I now draw a particular loop that I'm integrating over, so imagine now I am drawing, I'm integrating this like this. And if I do this consistently among the various different elements, and hopefully you should notice that the 2 adjacent elements here, 2 adjacent lines over here, are actually in the opposite direction. And so if I have a whole collection, again, if I do the following, if I have a whole collection of elements, then I do the sum over I, actually no, sum over, let's call these j's, and leave i's as the elements over here. So then I get all the sums over ci dot dl I like this, plus the sum over the curl of a over all ds i's. Okay, so all the different elements, and I'm summing them up. Sorry, j's. Do this. Then, both sides, if I now shrink this to infinity, both sides turn into an integral. But the left-hand integral, actually the right-hand integral is fairly straightforward, right? We've got all the different surface elements. And this just leads to the usual A and then ds. But as we've seen here, all the adjacent line elements, if you consistently, do the line integral in the same direction, they will be in opposite direction. And so just as the way we've seen it before, where for a particular volume, all the surface elements, adjacent surface elements, have opposite signs, and therefore their contribution cancels, we can say the same thing here, and we have that integral A dot dl here. In this case, this surface S is the total surface, right? So we've got total surface S, and then this C over here is simply the bounding contour of S. So in this case, just to make this illustration even more full, in this case, the bounding surface, and let's just use red, the bounding surface of this here would look something like this, where you have to imagine that all of these are connected. Okay? And then S is the entire red surface, and C is the line that bounds it. And so we end up here with Stokes' theorem, where we now can relate the curl of A, right, over some surface to the loop integral of A along its bounding surface. So practically, this also means that when we are integrating some curl, we can get rid of the curl by using Stokes' theorem. Let's take a look now at the last part, and that is, well, obtaining the last two field equations. Again, let's take a look at the field equations. Field equations. But now in the divergence for the cross. Hopefully these few seconds have given you a chance. So let's take a look at the electric field. Electric field. We know that the electric field has zero curl. Take a look. So I know that the curl of E dot ds equals to loop integral of dl, and I know that this equals to 0. And similarly, with magnetic field, I know that curl B dot ds equals the integral of B dot dl. And here, what do we have? We have here that this is mu naught j, mu naught, and I'm getting the integral of j dot ds is simply mu naught I, the current. Okay? Remember that if this is some density, this is some density j here, sorry, here this is j, and this is ds, and this is simply I. current that goes through. Okay, so now we have completed using Gauss's theorem and uses Stokes' theorem. We have completed the set of Maxwell's equations, but now for in the integral form. Okay. Let me quickly pause to see if there are any questions at this moment about the divergence theorem, Stokes' theorem, and the integral forms. Okay. I don't see any questions. So going once, going twice. How about second part in Maxwell's equations? What do you mean by second part of Maxwell's equation? The Why don't you just speak? All right. Feel free to speak. So, are you talking about the time derivative of e? Yes. Okay. Yeah. So that's the thing, right? Here we've assumed that everything is nice and static, and in the case when things are not static, then of course the field equations, even the differential forms are different. And so, this here no longer becomes the simple J, right? So the curl of B does not simply become, it's not just mu naught J. And there we'll have to add an extra term. So when we go to the dynamical situation, then we do have to add, we do have to add more terms. And then here, again, when we apply Stokes' theorem, then we will end up having to use additional terms as well. Okay, is that clear? Okay, let's move on. So there's two things I want to basically end with, and that is I want to go through one last result, and that is the current conservation. And also, I want to finish up something that we did last time around, where we couldn't finalize the proof of something. So let me quickly grab the current part out, and let's start with a consideration of the current. Second to get the notes out. Technology is failing me again. Okay, here we go. That works. Okay. So one thing I wanted to discuss is indeed charge conservation. And in particular, I want to find an expression for charge conservation that is actually going to be crucial when we consider the set of Maxwell's equations. So one thing that is very, it's almost like a fundamental assumption, is that we cannot create or destroy charges. There's no process, there's no physical process that allows us to do so. Now, we may have seen things like, we can create a proton and a positron together, and then basically end up with both positive and a negative charge. But then they have to come in pairs, right? And so this itself is embedded into a particular equation that I want to show. So the first thing that we want to know is that and this is that we've used before, is that the total charge Q is simply the integral of rho dV. Okay? Now, imagine the following. I've got a particular surface, okay? And let's say there's some current flowing out. I know this is I, right? It's just the current flowing out, which is given by J dot ds, if this here is ds. But I know this I, this current, is just the flow of charges. And so the second thing that I know is that dq dt, okay, let's just call this out, equals J dot ds. The total charge out some particular surface is just the rate of change of charge with respect to time and J dot ds. But I can equate this now to the first equation. It simply states that this is d by dt, or minus d by dt, of volume integral of rho r t. Okay, but this is just the surface, the charge density. And now I can combine these equations. Simply combine these equations to get conservation of charge, because I can actually put the differentiation inside and write partial rho partial t like this. Okay. Or I can now look at this equation over here, and I can turn this equation using Gauss's law to turn this into a volume integral. So this here, let me just use a slightly different color. This here I can also write equals to the divergence of J. So now, what do I have? Write the following equation, right? And I combine the green one, this green portion over here, and this portion over here. I bring them all to one side. I take out dv, so I can write that the integral of v partial rho partial t plus the divergence of j integrated over dv equals to 0. And indeed, here I can now get my final expression for the conservation of charge, which is just partial rho partial t plus divergence of J equals 0. This is the charge configuration. So as you can see, the use of Gauss's theorem is actually, allows us to write this J dot ds as the divergence of J over some dV, and then we can rewrite this as a charge conservation formula. This is just one particular example that I wanted to show of the use of Gauss's theorem. And the second one I want to show you is related to finalizing the proof that we had last lecture. So if you recall, and let me actually show you last lecture, slides of last lecture. So stop this one here and share this one. So in last lecture, we actually, in order to derive this mu, so like the curl of B equals mu naught J, at this one here, we looked at the divergence of r minus r prime over r minus r prime cubed equals 4 pi delta r minus r prime. And here I said J dot curl, dot nabla, r minus r prime cubed, this equals to 0. And I just, made some hand waving motions. Okay, it's because this ends up being a boundary term. And we can now use Gauss's theorem to actually prove this statement. The reason why this term actually ends up being 0. Stop the share on this side again, and here. So let's indeed complete. Let's complete the proof. So the point where we left off is the following. We have that J dot nabla of r minus r prime divided by r minus r prime okay. And so let's see if we can rewrite this. The first step, the first thing that we should note is that this nabla acts upon something that only the combination r minus r prime comes in. Well, last time we saw that if we operate this nabla on J, it equals to 0 because J is J prime, right? It's a prime. And so it's only defined in the prime coordinates. In this case, it both, this r minus r prime thing has both r and r prime. So we should be able to act upon using nabla or nabla prime. And in fact, because it only appears in a combination r minus r prime, we are actually allowed to write this equals to minus a prime, this is nabla prime, r minus r prime, divided by r minus r prime. Right? Because in this case, the transformation of this element over here, I can simply replace r. I can let r go to minus r prime and r prime go to minus r. But I need to put a minus sign here, right? I can flip the two, but only with the minus sign. And that also means that the nabla, in principle, can be flipped, provided I put a minus sign there. So that's what I do, right? I add a minus sign here. And now we have something that is able to, where we are able to operate on all the different elements. Sorry, this is again. Okay. So now we are in a position to rewrite this. And I'm actually going to use the product rule to write this as follows. I'm going to write nabla prime dotted with I'm gonna dot this with dot this with the following. Well, okay. Let's take a step back. So here, what we actually have is we see J dotted with nabla and then acting upon something that looks here, which is a vector quantity. And in this case, what does this actually mean? Well, because the dot product is already in these two. So here, what this effectively is here, this here in bracket, is a and I use air quotes because you shouldn't take it too serious. It's a scalar quantity. So this scalar quantity here acts upon the so-called vector quantity in a way that we have to separate them in the x, y, and the z direction in individual components. So another way to say this is that the thing that we consider x component, which is simply J prime dotted with nabla prime this, and then we've got x minus x divided by r minus r prime cubed. So that is the actual x component. And this thing is something that we can now rewrite, because I can write here nabla prime dotted with x minus x prime r prime by r prime cubed. I've got j prime minus x prime over r minus r prime cubed nabla prime dot j prime. Okay, so imagine the following. This is just a product rule. So I've got this nabla prime acting upon this first x minus x term, and then I've got the j prime term. And that gives me two terms, and I can rearrange that to get this expression over here. Okay, now one thing that is, I can now state this term over here, 0 for steady currents. If I'm talking about steady currents, then the divergence of the current is also 0. Right? There's only currents going in a steady direction in one way. But the divergence of J, right? There's no source in that sense of currents. The amount of current goes in and the amount of current that goes out is always the same. So that's the first part. Now this part here, remember before this was part of an integral. This is really the point that I wanted to make for this. The second part is a triple integral in V. Now we write this as nabla prime x minus x prime divided by r minus r prime cubed j prime d. And this is exactly the point that I want to make, because this here, you can actually use Gauss's theorem to write surface integral. Okay? Now we ignore the divergence, get rid of the divergence, and we can write r minus r prime cubed j prime dot ds. Prime if you want to be very consistent. And here, this is now the magic sauce. So imagine the following, right? In the left-hand side, it actually doesn't matter where I put V, right? I can make V as large and as small as I wish it to be, as long as I contain J, right? As long as J is contained, because If I'm outside of the region where J prime can exist, then J prime is simply 0. And this whole integral, that contribution does not add up. So this V here, made as large as possible, as large as desirable. And that also means that this S here can be, I would say, as far as possible, as far away as possible. But if S is as far as possible, then J, and the value of J at the surface, equals to 0. Here, and this is what I typically mean by boundary term. The right-hand side J, sorry, the right-hand side S is, let's say, at infinity, where J prime equals to 0. And so the integral vanishes. So this here, you can more or less see this as a boundary term. And that's why, and because I can put the boundary wherever I want, I put it at infinity, and I can get rid of this term. Okay, so this ends today's lecture, and let me see if there are any questions on the topic, and then again I'll close out the recording and we can continue. Okay, so open the floor to see if there are any questions. Let me also quickly go through the chat to see if there are any questions that were there. Okay, so Alex, quite early on, I more or less missed this. Should we also specify that if f goes to 0 at infinity, then f is completely determined? Recall the case of adding constant vectors to f. So in Helmholtz theory, it is not necessary. F goes to 0 at infinity. So whether it is completely determined or not is not dependent on whether f has to go to 0 at infinity. I believe there was another question. My memory is failing me a little. There was another question about.
Yes, the a theta a and then times nabla dot nabla will equals to 0.
Okay, yes. So let me pull out the slides again. This, stop sharing here and start the sharing here. Share. So the question was, I think the following, right, is if I have a nabla here and I do all of these terms, then what you'll see is that actually these terms here vanish. Right? This term here vanishes, and this term vanishes, and you only get this term and this term. Check if that is correct. And indeed, I get a, and we get this one. Okay, yes, indeed. So, indeed, if this was a nabla and this was a nabla, or if this is a nabla and this is a nabla, then you're actually not operating on anything, right? And that is counter to what you are supposed to do, because here you have a nabla acting on A, which here, this here by itself is a vector field, and then we have something that is then another, another curl of a vector field, which again gives you a vector field. The problem is that if you put a nabla here, or if you put a nabla here, then what you end up is not a vector field. This is just an operator, and you end up with something that is still by itself an operator, and therefore these terms, if you will, don't exist. Of course, you can explicitly do the calculation and show that they don't exist. If anything, I think they even cancel. They may, if you actually just do them outright here, then I think these two terms end up canceling. I need to double check, but if you actually do the algebra, then these two terms cancel. So it's not even necessarily that they don't act upon anything and therefore they must vanish. It really is just they it's nothing physical, because here you end up with an operator, but the actual algebra, I think I'm pretty sure these two end up canceling. But I do encourage you to try this at home. Okay. They do not appear. Okay, yeah, that's. I don't know whether they vanish. I end up writing it that way. Don't they end up vanishing? Vanish. Anyway, it's not too important in this case.
Okay, thank you.
Anyway, any more questions? More questions? Okay, let me indeed stop the recording now.